soluzioni spaventose. Proprio con un duplice uso. Però ha avuto un attimino di... No, non è solo questo. Allora, sì. Proprio perché lei aveva io erano i mani spalle, erano non canzonari, non è che mi fosse il presidente così non lavoro. No, mi passa il 20.
Good morning.
No, anche questo è particolare. Per quanto meno non c'è.
Okay, so today we are going to do some theory and practice with Python. So please download exercise number 3 and 4 from Virtuale. So there is new number 4, that is about deep learning, and also the number 3, since we are going to see how it's possible to implement a multi-layer perceptron with scikit-learn. Okay, and also we have to spend a few minutes to do the investigation about the course. So please scan the QR code or use the code and provide the questionnaire. I give you about 5 to 10 minutes to complete the survey, okay? On Virtuale, the numbers are 3 and 4. I can check if, oh, something worked. Okay, something went, I have to upload number 4, okay? Since I upload before, but maybe I don't have saved the upload, sorry. So I upload the number 4 while you can, in the while you can do the survey. Sorry for that. Okay, now there is also the exercise number 4. So I put another time. Oh, I forgot. No? Do you prefer light on or what? Okay, have you finished with the survey? Okay. Okay. Have you finished? Okay, so we can start the lesson of today. So we are going to recall some elements of the last lesson, since this part is really important. Okay, this is the only possibility to see deep learning during your DTM course. So we are going to focus on the main elements, and also during the final exam, a lot of questions will be about deep learning, of course, since it's one of the most important parts. Okay, also about machine learning, but also about, of course, deep learning. Okay, we have seen that the fundamental element of deep learning is the artificial neuron. Okay, and we have seen that with the artificial neuron, we are going to emulate the neuron of our brain, the human brain. Okay, so we have many inputs. We have the cell body. Okay, we have many inputs. For example, we have numbers in input. So here, x1, x2 until an n input xn. Okay, so we have number in input. Then these numbers are weighted. Okay, so here for x1 we have w1, w2 until wn. Okay, so input weights are very important. So remember the word weights. Okay, then here we apply a sum. We sum all the elements with their weight. Okay, so we collapse, we merge, we sum all the inputs in a weighted manner. Okay, this is a sum with weights. Then we add a constant, a value that is called bias. Okay. Then what else? Here we apply, before the output, we apply an activation function that is a sort of switch. Okay. Through the activation function, we can enable or disable the output of our artificial neuron. Okay, this is really important since this structure reflects the structure of the human neuron. Okay, in which we have input, weighted input, we have a cell soma, the cell body with a nucleus, and also in our brain there are many switches, different switches that can turn on or turn off our stimulus. Okay. And we have also seen that with only a single neuron, artificial neuron, is possible to solve only simple problem, in particular only linear problem. And this is a problem. Is a problem similar to the SVM, if you remember. With the standard SVM, we can solve only linear problem. So the solution with SVM is apply a map function called through a kernel. Okay, we can map the data from a non-linear space to a linear space. With artificial neuron, we don't use, the solution is not using a single neuron, but a network of neurons. Okay. Also in our brain, scientific studies has shown that the intelligence, the human intelligence, is related to the synapse, the connection between different neurons, not the neuron. Okay, the neurons are important, of course, but the real intelligence, the concrete intelligence, is the connection between different neurons. Okay, when we learn something, we create new connection. When we forget something, we destroy, we disable connection. Okay, that's why connection also with the artificial neuron are so important. So we use network of neuron, as you can see in the central part of the slide. In particular, here we are seeing a multi-layer perceptron. Okay, multi-layer. The meaning is that we organize neurons in layers. Since we want to organize, we have connection between these layers, and also these layers are ordered. We have an input layer, an output layer, and one or more hidden layer. In this case, only one, but we can have more than one hidden layer. Okay. Usually, if we increase the number of hidden layer, we increase also the ability of the network to solve problem, to get more accurate results. But also we increase the computational load, and that's a problem since neural networks are require a very intensive computational power, okay, very strong computational power. That's why we are forced to use GPUs with neural network, and in particular with the second version of this neural network that is called convolutional neural network that we are going to see next lesson. And okay, in this slide you can see the intuition, the general intuition about the neural network training. And that is very important. We are going to see, we don't see many math equation function, okay, they are out of the scope, but now it's very important to understand the general behavior of the training of neural network. Okay, we have input data, of course, in input, and these data usually are divided in mini batches. So we learn from little group of input data. Then we pass this data with a forward operation through the network, and we obtain the output of the network. Okay, so we obtain that. Then we compare the output with the ground truth. What is the ground truth? Is the label, is represented by the labels that we have, since we are using annotated data. We are in a supervised learning scenario, so we have annotated data. So it's very important to compare the output of the network with the ground truth value. This comparison is done through a loss function. The loss function is one of the most fundamental elements in the neural network training, since this represents the goal of my learning activity. Is the mathematical formulation of the learning activity. Okay. With this formulation, we indicate to the network what is the scope of its learning. Okay, so it's very important. Through the loss function, we can compute the error. We can understand what is the error between the prediction of the network and the ground truth, okay, annotation. And then we can use the error to change the weight of the network, okay, not only the single neuron, but the weight of the network. And then we can repeat this process until the error is decreased, okay, under a certain threshold. So the training of a neural networks is strictly related to the minimization of the loss, or also called cost function. Okay, if we reduce the error, if we minimize the loss function, we are training the neural network in a proper way. Okay, and okay, in this slide we have discussed the fact that we use different loss functions for different tasks, and in particular here you can see the loss functions for the classification task, and we are going to see, for example, the loss functions for the regression task. Okay, so remember that for a specific task we have to use the specific loss function. Okay, we cannot mix loss function or something similar for classification task. We have to use loss for the classification task, for regression, loss for regression. Okay, we have seen that we can apply this function, in particular the loss function and the cross entropy function, if the output layer output probabilities. And so remember that this value is called logit. If we apply the softmax, we obtain probabilities, okay, in which the sum of all probabilities is equal to 1. This is very important, since we pass from numbers, logits, to probabilities. And if we have probabilities in output, it's possible to compute the cross entropy loss function. So that's why it's so important to remember that we need the softmax activation function in the softmax layer in the final part of our network. And okay, here we have seen a real example. And we have seen some math, since how it's possible to minimize the loss. We can use the weights and the bias, okay? So these elements are involved in the network training, also the bias, and what we focus in a specific manner on the weights. So the weights are the most important part for the network training. And then we can adjust the weights using the gradients, so the derivative of the loss function. So the loss function is a function, a mathematical function. So we can apply the gradients, we can compute the derivative, okay? So using the gradient is possible to understand if we are increasing the error or we are decreasing the error. Okay, remember that the gradient, if we have a function, the gradient tell me the direction of the function in a specific point. So we can use the gradient to understand if the error is increasing or not. And then we have to follow, of course, the direction in which the error is decreasing. Okay, since if the error is decreasing, we are minimizing the loss function. And then we are training in the proper way our network. Okay. Here you can see also the formula, the equation that we use to update the weights. There are many equations. This is one of the most simple. So the new weights, the W with the trait on the top, is equal to the old weight minus eta and what? The derivative of the loss function over the weights of the network. Okay. The element, the Greek letter eta is the learning rate. That is the rate of the learning of the network. Since using this element, we can weight the change in the weights. Since the weights, the new weights, are equal to W minus eta. And then with this value, we can vary the quantity that we subtract from the old weight. So we can regulate the learning rate of the whole network. We have seen many different optimizers that are the gradient descent approach. If we use gradient to reduce the error, this procedure is called gradient descent approach. Okay, I don't know why it's not working in certain part of the blackboard. Okay, and then we have seen that one of the most important optimizer is the stochastic gradient descent, since with the stochastic gradient descent, we don't use the whole dataset in input to compute the gradient. It's not always feasible. In particular, if we have huge training dataset, it's not possible to load all data in RAM memory. So we are forced to divide the dataset in different batches. And that's why usually we use SGD to optimize our gradient in our network. Okay. Try to write in a. So for example, in the code that we are going to see later, it's possible to choose the optimizer that we want to use. For example, you can specify SGD, that is the stochastic gradient descent. But for example, you can also define the Adam optimizer that is similar to SGD, is based on mini batch of data, but require less input parameters, so it's more easy to be used. And what else? Okay, backpropagation is the way on which we compute the gradient. We have to compute from a theoretical point of view the loss with respect to all the weights of our network. And this is possible only with one layer of neuron. Otherwise, it's not possible. If we have one or more hidden layer, we cannot access these elements, since it's not possible to put the loss function in direct relation with the weights of the hidden layers. Okay, so what we can apply we can say a mathematical trick called backpropagation that is based on the chain rule. So you can see that for the final neuron, we can compute the derivative of the loss function with respect to the weight of that neuron. That is possible to compute this quantity using the derivative of the loss with respect to the output of the network, multiply with the derivative of the output of the network with respect to the weight of that neuron. All elements that we know in the final neuron. And then we can apply this procedure for every neuron that is available present in our network. Okay, so the backpropagation is compute step by step, starting from the last part of the network to the initial part of the network. That's why the name backpropagation, since we go from the final part to the initial part. Okay. Remember that backpropagation is a local process, as you can see here, we use only the components that we have in a specific neuron. So it's a local process, and that's why we can apply backpropagation also in the hidden layers. And also in this case, neurons are completely unaware of the complete topology of the network. And then you can see that for the training of our networks, two steps are very important, are fundamental. The first step is the inference, is the so-called inference or forward step. The forward step is when we provide an input data and we obtain the output, okay? So remember, forward step or inference. Then when we compute the error through the loss function, and then we apply the backpropagation algorithm, we are apply the backward step procedure, okay? Since we are going from the back to the initial part of the network. And this is the proper phase of learning, is the proper learning phase. Okay, do you have question about that or not? This one? Okay, we use this formula to compute the new values of the weights. So the new values of the weights is computed using the all weights, and then we use the derivative of the loss function in order to minimize, using the decreasing part, minimize the loss function itself. Okay, so we follow the gradient in order to update our weights, in order to minimize the loss function. Okay, we have also these parameters that regulate, we can say, weights the importance of this subtraction. Okay, based on, we are going to see, it's possible to define different learning rate. Usually we use small learning rate, but it's not mandatory. We can try in our exercise to vary the learning rates. Okay, there is not a general rule that we can follow to apply to get this value, but usually it's small. Usually we can set 0.001 or 1 or 0.001. We have to try. Okay. From a general point of view, in deep learning is hard since there are no general rules to follow. Okay, it's hard since we have to use our expertise to define, for example, the learning rates, to define, for example, the loss function, to define, since there are many loss functions that we can use, so we have to choose the best one. We have to define what is the optimal optimizer. Okay, and there are not general rules to be followed to follow in order to get the best results. That's why it's so important to practice with deep learning using the same code and varying some parameters. No, that one. I think no. It's better to say that is the rate of the learning, since if here we have 1, we have a very fast learning since this parameter is multiplied with 1, so it's the same. But if we multiply this parameter with, for example, 0.001, we are decreasing a lot this parameter, so we are changing in a very small part the old weight. So it's the learning rate. Okay, is the name is the best definition, I think. Okay. And let me open a slide since I have a GIF. I prepare a GIF, but in PDF is not possible to see the GIF. Okay, here. Okay, this is the following slide. So but this is a GIF, so it's not possible to visualize, of course, the GIF on the PDF. So I'm going to show you the PowerPoint. The optimization procedure, that is the learning process, okay? The optimization is the optimization of the loss function. So if we optimize the loss function, we are training our networks, can be represented from a visual point of view in this manner, okay? So let's start from the first step. We have a surface with different colors, okay? Blue colors denote low values. Red, yellow, orange colors denote high values, okay? And this surface is the solution space of the loss function. Maybe you know that it's possible to represent mathematical function in a defined space, okay? In your high school, I think that you have learned to represent a function in the 2D chart, okay? In the 2D graph, okay? In this case, we are representing this function in a 3D space, okay? It's the same. So we know that the loss function can be represented by this 3D surface. Of course, in blue color, we have low values. So the meaning here is that we have low error, since if this is the representation of the loss function, low values correspond to low error, okay? Why? If we have high values, we have an high error. Remember that we are discussing the role of the loss function, okay? That is connected to the error, okay? Then we have second step. We have a starting point that is the first red circle. The starting point represents the output of our neural network using an initial configuration of the weights. In the beginning of the learning phase, these weights usually are randomly set, okay? So we have random values here. We don't know what is the optimal values for W1, 2, or N. So at the beginning, usually we have random weights. So for example, here we have 0.5, here we have minus 1.2, here we have 0.72, and so on, okay? We have random weights. So we take input data, we apply the forward procedure, we obtain the output, and then we put this output on our loss surface. And this output is represented by our first red circle, okay? This is the starting point. This is the starting point of our learning process. We know that the desired point, the goal of our learning activity, is the point that you can see here, this part. Is not okay. Here we have blue colors, so this is the global minimum of our function. So we want to achieve this point in order to optimize our loss function. So we have to identify the path that we have to follow in order to go from the starting point to the global minimum. Okay, how is possible to do that? We compute the gradient of our loss function, and then we follow the direction of the gradient that minimize the value of the loss function. Okay. And then we have the second red circle, the third red circle, and so on. Remember that this is why the learning procedure is performed in an iterative manner, step by step. So we have different weights, and then we are iteratively adjusting the weights, and then we can iteratively reduce the loss function and then the error of the loss function. And following the gradients, we are able to achieve the global minimum, okay? You can see that also the distance is not proportional in the sequence of red circles. And the distance between two red circles is the learning rate. Okay, that's why the learning rate is very important, since if we have a too big learning rate, maybe we pass from that point. Sorry, but I cannot use my pen on the slide. If we use a very huge learning rate, maybe we pass from here to here, since we have a very, very big step. So from here to here, for example. And if the learning rate is too small, it's not possible to achieve the global minimum in a suitable time, since we need a lot of different steps, and this is not easy. So we have to follow to find also the optimal learning rate. Okay, usually you can set learning rate, I repeat myself, 0.001, 0.1, and similar values. Okay. Okay, unfortunately, we have also some local minimum, since, as you know, with a generic loss function or with a generic function, we can have different minimum. So we have one global minimum and several local minimum. So if we achieve the point of local minimum, okay, we have optimized our loss function, but maybe this is not the best solution that we can have. And usually we can try to repeat the learning procedure in order to obtain the global minimum instead of the local minimum. Okay. Remember that usually we start from a random weight. So if we repeat the procedure, we randomly create new weights, and then we create a new path in our surface, and then maybe we achieve a different point. That's why it's also important to repeat the learning phase procedure. Okay, or another solution is to start from pre-trained network. Okay, network that are already trained by I don't know, a lab in a university, by a company, trained on a specific data set, and then we can fine-tune the network using a small learning rate, updating the starting from the weight compute on a different data set. That's okay. But we are going to see how it's possible to use a pre-trained network, okay, in the following step. Okay, do you have a question about that? I know that is not so simple, but maybe you can read another time the slide, then you can ask me something, and then we can try to explain another time the training procedure of neural networks, since I know that is a bit complex, but since there is a lot of math behind it, and without math, is quite difficult to understand all the steps. Okay, but also the math is very complex, so we have to find a compromise. Maybe we can see together this slide that is a summary of the whole training procedure. Okay, so we can see if you have understood or not the training procedure. Let me drink some water. Okay, so to summarize our neural network training, we start from the most important element after the data, that is the loss function. Okay, I think that now you have understood that loss function is one of the most important elements in our network training. We start from the loss function. We want to try to train our neural network. The meaning is that we want to minimize the loss function. We want to reduce the error. We want to move close to the goal. Okay, we want to reduce the error between the prediction of the network and the annotation, the ground truth annotation. First step, first consideration. Okay, loss function, minimize the loss function. How is possible to minimize the loss function? The only thing that we can change in our network are called weights, okay? So we can change the weight and also the bias to change the output of our network. So
The weight and the bias, right?
the weight and the bias, okay, yeah. Yeah.
The bias.
Bias is an external value that we add to the sum of input. Is derived from a biological consideration, so it's not important. We only know that there is a value that we add to the sum, okay? Is a biological, derived from the biological, since we have also external stimuli here that we have to add directly without any weights, okay? From a biological point of view. From our point of view, we have a weight that, a value that we add inside the cell body. That's all. No, we don't see any. It's quite very similar since we have to apply the derivative, the gradient, and then we change the bias.
Would be like D minus.
Yeah, something similar. Yeah. So that's why I say that we focus on the weight to simplify the context of the tree. Okay. So there is also the bias, but we focus on the weight. Okay. So we can adjust the weight to change our output. And we adjust the weight using this formula. Okay, so new weights are computed using the old weights and what? The derivative or the gradient descent technique. We use the gradient descent technique, this concept, to minimize the error inside our loss function. Okay. To minimize, to apply the stochastic, the gradient descent, sorry, we have to apply an optimizer that is a way to reduce the error using the gradient descent technique, okay? This tool is called optimizer. We have seen the SGD optimizer, the Adam optimizer, and so on. And in this case, the optimizer have different input parameters, such as, for example, the learning rate, but we can have also the batch size, that is the size of the input data that we have in for every steps and so on. Yeah. The optimizer is the implementation of that formula, we can say in very simple words. Optimizer is a way to reduce the error using the back propagation and using the gradient descent technique. Okay. This is an equation that indicates that it's possible to use the gradient descent technique to update the weights, and the implementation is the optimizer. Okay. The optimizer is the tool that we use to optimize the loss function. Yeah, for a single step of batch of data. Yeah, perfect. Okay. The gradient descent technique is based on a very important algorithm that is called back propagation. Okay. And that is based on the chain rule. Back propagation has been introduced in 80s, in 1987, if I remember well, by 3 people. In this group, there is Geoffrey Hinton, that received the Nobel for computer science, and the name of the Nobel for computer science is the Turing Award. Okay, so it's a very important contribute to the scientific community, the back propagation algorithm. So we can apply the back propagation based on the chain rule in order to apply the gradient descent technique in order to minimize the loss function. That's why, and this is the novelty here, is the final element. Since we have to apply the gradient descent technique, the loss function must be derivable, of course. Since we have to apply gradient, so the loss function must be derivable. We need to apply derivative on the loss function, then the loss function must be derivable. Okay. You can see also the effects on the right of using different learning rates. So you can see a 2D graph. In the x-axis, we have the epochs. The epochs is the number of different iterations that we have during the training phase. In the next slide, we are defining in the proper manner what is an epoch. Okay, but okay, here we have in this chart. Here we have epochs. So the first epoch, then 2, 3, and epoch. Remember that the learning procedure is an iterative procedure. Okay, we apply many times the same procedure in order to learn the right weights. So we have many different inputs.
So it's like a cycle.
Yeah. Remember the slide of general paradigm of, okay, is a cycle. We repeat again the same procedure. Okay. In the y-axis, we have the loss value, the error, we can say also. Okay. And then you can see that the starting point is here. The starting point, remember, is a network with random weights. Okay, so the weights are set randomly. We don't know anything about the weight. And then we have a certain error here. If we iteratively apply the procedure, the learning procedure, we can decrease the error following the gradient. And that's why, for example, applying the procedure, we can obtain this curve that indicates that across different epochs, the network is able to reduce the error. So the network is learning. If we apply a very small, for example, this curve is obtained with, I don't know, 0.01 learning rate. If we reduce the amount of this learning rate, for example, we use eta equal to 0.0001, we obtain a curve that is in this way, very, very slow. Okay, maybe we can achieve the same final error here and here, but after many epochs, since the learning weight is reduced. If we apply a high learning rate, for example, we have a curve that in this way, or even in this way. If we use a too huge learning rate, for example, we pass from this point but the step is too huge, and then maybe we can go in the second step we go here, and then we go here. We have two huge steps, and then we are not able to achieve the global minimum. So, for example, after few iterations, after few epochs, the error is stable, or also in a very negative manner, the error is increasing since we are not able to achieve the global or the minimum, the local minimum, but only the highest value of the function loss, the loss function. Yes. 10, for example. One is not so common in deep learning. Okay.
Times maybe at higher values we get negative. So I'm trying to apply to the for you.
But it's better to apply the reasoning on the surface. Imagine that the learning rate is the step on which you move over this surface. If you are not able to go into the global or the local minimum, since the step is too big, you are not able to achieve the lowest result. So you have to find the proper small step. The positive thing is that, okay, with SGD, you have to define the learning rates that is used for all the training procedure. The same learning rate is used in the SGD. So if you define 0.001, this learning rate is the same for all the learning procedure. With Adam, you define an initial learning rate, for example, the same one, 0.001, but Adam is able to change this value automatically. So that's why Adam is very useful to train neural network if you don't have a lot of expertise about deep learning training. Yeah, they only once at the starting of the with the same learning rate. Yeah.
We change it manually, or it's the software?
Automatically by the software. Right. Yeah, but if it is too high, too big, is not good for the automatic decision. So you have to start with feasible values. Okay. There are many other differences, but if you are interested about, we can discuss later, since the use of different optimizer is very specific and also is very hard. Okay. We are working on finding new optimizer in our research work. So, okay, it's not so easy to understand all the conceptual elements behind Adam or SGD. Okay. But if you are interested, I can suggest you some papers or something similar. Okay. Maybe you are interested. Okay. So we have finished the part about deep learning with multi-layer perceptron. Okay, note the difference. Now we have seen how it's possible to train multi-layer perceptron. So single neural neurons, artificial neuron, put together in a network with different layers. Next time we are going to introduce convolutional neural network. Okay, so you have to remember this difference. Okay, multi-layer perceptron are different with respect to convolutional neural network. That is a new typology of network that we are going to introduce in the next lesson.
How is this called?
Multi-layer perceptron. Okay, you can find also on the slide. Okay. So some terminology of the training. So batch size. The batch size is the number of training sample that we give an input to our model. Okay, so the optimizer used these samples to find the optimal gradient to be followed. Okay, so the batch size is the number of training samples that we have in input. Okay, typically we can say also here the batch size is not easy to say what is the the best value for the batch size. Okay, there is not a general rule to follow, but we can say that usually batch size is a multiple of the power of 2. So for example, we have 16, 32, 64, and so on. Be aware that if you choose a very small batch size, you can compromise the stability of the learning phase, since you compute the gradient on too few elements. So it's not possible to compute an accurate gradient, okay, of the loss function. But be aware also that if you use a very big batch size, a larger batch size, you need a lot of video memory on your graphical processing unit if you are using a graphical processing unit. So it's not possible to use, for example, a very huge batch size on a GPU that has a limited amount of video memory. You can check the technical specification of your GPU if you have one on your desktop in the setting tab of your operating system. And from empirical point of view, we can say that in classification problem, the number of classes must be equal at least to the number of samples in our batch size. Okay, so if we are tackling a classification problem with 5 different classes, at least we have to have 5 different samples in our batch size. Okay, it's an empirical rule. Then we can introduce the iteration. The iteration is obtained by using the size of the training set over the batch size. Okay, so if we have a data set with, I don't know, 100 of samples, the batch size is 20. The number of different iteration is 5. We have to repeat for 5 times batch size of size 20 to pass all to process all the training data that we have in our training data. Okay. When we have seen all the example in our training data set, so we have applied for 5 times batch size of 20, we have an epoch. Okay. And if you remember, here we have used the word epoch. Okay. So for each epoch, we have seen, the network has seen all the samples that are in the training data set. Okay, so one epoch means that each sample in the training set has the opportunity to update the weights. So we have used a specific sample, all the sample, to update the gradients of the loss function and then to reduce the error of the loss error. And okay, an epoch, of course, is comprised of 1 or more batches, since we know that the iteration is the size of the training set over the batch size, and the number of epochs is traditionally large. So usually we repeat the iteration learning procedure for at least 10, 20, 30, 100, 1000 times. Okay, and that's why the training process is very long. Yeah.
In the case of so like the 100 and then 5, so we have 5 opportunities to change the weights or not?
In that case, yes. Since you change the weights using the gradient compute using these 20 samples in it. Right. The epoch. Okay, when we have the epoch, when we have seen all the training data, when we have used all the training data in input, we have an epoch. So if we have 100 of training data and we are using a batch size of 20, after 5 iterations, we have an epoch, since after 5 iterations, we have seen 100 samples. Okay. Okay, last slide of today. The last one is very simple. It's the slide about shift-learn. Usually during the training process, it's very common to create line plots that show these elements, okay? That show the on the x-axis, we have the epochs. On the y-axis, we have the loss error, okay? The error computed with the loss function, okay? And usually, let me define a new graph. I don't know why it's possible to use these markers. Okay, so usually we create 2 different plots, one for the training and one for the validation. You remember maybe that the train set is divided in train and validation. And then we have the test set. And usually we put the majority of data here, around 60, 80%. And in the test set, we put the remaining 20%. Okay. We use the training data to train our model. And then we can plot the curve of training data. Okay. And then after each epoch, we can also compute the accuracy, the error produced by our network. So remember, on validation data, we use the validation data to understand, to compute the error produced by our network after each epoch. And then we can plot also this curve. So we have here validation and here test set. Sorry, train. These two plots are very important, since using these two plots, you can understand several ways, several elements. The first element is the black curve that indicates that the training phase is okay, since the error is decreasing. That's okay. Second element, the validation curve, the red curve, is also in this case okay, since also in this case the error on the validation set, the error is decreasing. That's okay. So the meaning is that the learning process is conduced in a proper manner. Okay. Then we can understand also if, for example, our network is overfitting. Okay. For example, as you can see here, we have a point in which the train curve is different with respect to the validation curve here in these points. Here, when we have a divergence between training curve and validation, here, usually in this case, we are our model is overfitting. The meaning is that our model is not able to improve the accuracy on the validation set, is only able to improve the accuracy, to reduce the error, only on the training set. So the training data, we can say that the network is only focused on training data to solve the problem, the classification problem with training data, without taking account the validation data. And that is a problem, since this is not a good behavior. Since here, for example, the model is able to classify only the training object, only the training samples, and not the validation sample. So when we have a curve like that, we have to stop our training procedure to invest in this part. That's why it's important to plot this curve. Then we can analyze this curve, and then we can, for example, use the weight produced in this specific epoch by our training code. Okay. For example, we can save the weights of our network after each epoch. It's a common way to save weights. Okay. After each epoch, I save the weight of my neural network. Then I see these plots, and then, okay, here I can say, okay, here there is an overfitting phenomenon, so I have to use the weight produced after the 100, not the final, the weight obtained in the final epoch of my system. Note here the number of epochs. Remember that we can add a lot of epochs, 100, 200, or also 500. Okay. Don't worry, since we can use an automatic procedure in order to plot these two facts. Okay, so we use automatic procedure. Yep. Validation. Yeah, we have usually higher error in the validation and lower error in the training.
Whereas we should have the same.
Yeah, or very similar, very close. There is also the underfitting problem, but we know only the name, since the underfitting problem is not common, so common in deep learning. So I mentioned you only the overfitting problem, okay? Since usually the overfitting problem is when happens when we have a model with a network with a lot of neurons inside, million or billion of neurons, but we have only few training data. This is the common case to produce the overfitting problem. Since we have a too strong model, too many neurons, and too few training data. So the model is not able to generalize the knowledge, the learning process, also on validation data. Underfitting is not so common, so we can skip the underfitting error. Yep. Sorry. You have to wait more time. Yeah, for example, you can stop during, this is an example. In this case, you can stop, for example, your learning process. And then you can save a lot of time stopping after the 200 epoch, the learning process. You can also decide to have a lot of epochs. You have to wait the time for each epoch. It's not very, yeah, can be a problem. The model, sorry, Ken?
Every time that each weight is updated, or the model learn this way to start.
I don't have catch the core of your question, I think. Since maybe we can do this thing. We can have 5-minute break, then we are going to see the code, and then you can discuss with me this question, and then I can provide the, okay? So see you in 5 minutes, and then we are going to start the coding part. So download the exercise number 3 and 4, okay? And then we can discuss the question. Devo fare 5 misurare, ma non al più che vale a cambiare i valori dentro. Rimane tutto.
Sì, ma trovo paradossalmente nessuno di quanto è venuto siamo 15 persone che ci sono. Sì, anche se già facendo il culturale che io la macchina ce l'ho, però poi dopo vado a casa. Esatto. Quindi qualcuno con me può venire, però. Io non ho questo. Sicuramente in questa sala, io pensavo di andare in macchina, poi dopo marketing a casa, quindi non tornare a cedere.
Ma questo devi rispondere te, prima sul programma del testo ormai.
Vedi? Anch'io la voglio.
Devo vedere se ne ho l'acqua. Video ci faccio vedere una finestra brevi. Loro hanno fatto no, esatto, io vado con le ripetizioni degli altri, io mi capisco. Non ho io ho guidato queste nostre potete insegnare e poi quanto sono tanti di andere non ce lo so poi dopo sono confident Francia mi piace da morire faccio le per il caos.
We can start with the collab part.
Solo perché abbiamo cose buone più.
Okay, well, if you want to use a multi-layer perceptron, you can choose to follow two different directions. The first choice is to use scikit-learn. The second choice is to use TensorFlow. Okay, so if in your project you want to use a multi-layer perceptron, I repeat, you can follow two different ways. The first way is to use the scikit-learn package, and in this case, that's why you have downloaded the exercitation number 3. Okay, and as you can see here, we know this code since we have used this code the last time, and you can see that the only difference is that here we have to import the MLP, that stands for multi-layer perceptron classifier, from the sklearn neural network module. Okay, this is the package scikit-learn, and in this package we have the package neural network, in which there is the implementation of the MLP classifier. Then all the code is the same, while here, as you can see, we define not the, for example, the SVM classifier, but the MLP classifier. Okay. And okay, I have uploaded the Euclid dataset as usual, so I can show you this code. So here I import all the libraries, and then I set the random seed in order to have deterministic experiments. Then you know that this is the class in which I transform the label in numbers. So triangle is 0, square 1, rectangle 2, rhombus 3. And then here is the function that compute features, OG features, LBP features, or just the unroll image has feature. Okay. And then here, okay, here there is the dataset path, in which I have 0 images. What? Oh, okay. I forgot to unzip data. Then I run this code in which I get all the image names. In total, I have 800 names of the image. Then here I create the partition of the dataset. In particular, the training, I create the training partition using the 60% of data. Then I create the validation partition using the 10% of data. And finally, the remaining 30%, I put the remaining 20% of data, 30% of data in the test set. Okay, so you can see that we have split the 800 samples in the majority in the train, then we have the validation, then we have the test. Here is the code to extract the features. Okay, so here I have to specify the feature that I want. For example, I can put OG feature, and then this code produce all the OG features from the training, the validation, and the test data. So I have to wait. Okay, it's quite slow, unfortunately. Here I have to declare the MLP classifier. And if you go on the official documentation, you can see that this is the official documentation of the MLP classifier. You can see that there are many different parameters that you can have in input. For example, here you can see that the first parameter is the number of hidden layer. And you know what is the number of hidden layer? Is the number of layers that are not in input and in output. So here you can specify that, for example, you want two different, the number of neurons inside the hidden layers, okay? So for example, you can specify by default, there are 100 neurons in a single hidden layer. If you specify 100, you are specifying that you have two hidden layers with 100 of neuron in each layer. Okay, so this is the parameter that allow you to change the architecture, the organization of the artificial neuron in your multi-layer perceptron. Okay. Here you have the activation function. Okay, that is the maybe you remember the switch that we put before the output of our neuron. And then, for example, we have the identity, we have the logistic, and then also we have the ReLU that we have seen last time. Okay. Here we have the so-called we have called this element optimizer. In scikit-learn, the name is solver. Unfortunately, it's different. And as you can see here, we have three different optimizer. And okay, we have this first one, okay, that is out of the scope of this course, but we have also SGD, that is the stochastic gradient descent that we have seen before. And also we have Adam. And by default, you can see that Adam has the optimizer, default optimizer, okay? Then we have batch size, okay? We can change the number of training sample in input in the mini batch. Then we have here the learning rate. We can define a different learning rate, okay? We can say that by default is constant, but we can also define that the learning rate is changing across the training procedure. And here in the following, the learning rate init, that is the initial value of the learning rate that we want to use. Okay. And then we have many other functions that you can see in the verbose function. I put here in the code, as you can see, the verbose equal to true. We use this element to see the progress of the training phase. So it's quite useful since we can see for each epoch the value of the loss function. And then we have many other input setting that we can use as default setting. But you can see that is not so easy to prepare our multi-layer perceptron since we have many choices that we can have. Okay, so in this case, I use a multi-layer classifier with all the settings set to the default value, okay? The only thing that I specify that I want a progress of the training phase. And as you can see here, I can start my training phase. And for each iteration, in this case, scikit-learn print the loss for each iteration, TensorFlow for each epoch. So this is a difference. For each iteration, we have the loss value. And as you can see, the starting point have a quite high loss error since we have 1.2. And after few iterations, you can see that the network is able to reduce the error produced by the loss function. So here we have 0.7, 5, 3, and then here we have 0.06, 0.01, and then here 0.003, and so on. Okay, so after all these iteration, we have our final multi-layer perceptron train. Now it's possible after the training phase to validate our multi-layer perceptron, and we can see that the result is pretty good since we have an accuracy of 0.8. That is quite high. Okay. And then, of course, we can also predict we can use the prediction of our model to get the final accuracy compute on the test set. Okay, so you can see that with this model, it's possible to have a final accuracy of 0.76. Probably you will obtain a different accuracy since the initial point of our network is random. Okay, so I obtain an accuracy and then you can obtain another accuracy. Okay, is normal. So you can use this code to play with MLP. Okay, so you can use this code to change, for example, some input parameters. You can also try to have, for example, to use the MLP with different features. You can try to use MLP with unrolled images, with LBP features, and so on. Okay, so you can try to use different configuration of the same LP to see how it's possible to improve or also decrease the performance. Okay, and okay, we have 10 minutes, so maybe we can see also the code, the new code. So remember that you can implement MLP using the scikit-learn, but also the TensorFlow library. Okay, with the TensorFlow library, you can define in a more specific way the architecture and other details about the multi-layer perceptron, while with the scikit-learn package, you cannot decide all the details of the implementation. Okay, so the scikit-learn is more easy to be used since you can see that is we have only to declare the MLP and then fit the MLP and then predict, use the trained model to predict the output, and that's all. With the TensorFlow is different. So we are going to introduce a new tool that we are going to use in the following lesson. Okay, so now we can start to see the code, and the next time we can dive into this code so we can see from a very close perspective the use of TensorFlow library. Okay. Remember that we are going to use our TensorFlow library with Keras. Keras is a sort of wrapper of TensorFlow. It's possible to use TensorFlow in a very simple manner using Keras, since Keras simplify the use of TensorFlow to build our neural network and also to train our neural network. So the first thing to do is to connect the virtual machine and also import the library. Okay. And then we have to upload our Euclid dataset as usual. So I can select from here the Euclid dataset. And after the upload, I can unzip the Euclid dataset. On the left, you can see that the folder named Euclid dataset has appeared here. Okay. Then with TensorFlow, the loading of data is handled by the so-called data loaders that are specific function of TensorFlow and Keras that are able to load our training, validation, and test set. Okay, so you don't have to write the code to load data. To load data means that, for example, here we have to write the function to get the labels. We have to write the function to extract features, in particular to open the image, to resize the image, to compute a specific feature. With TensorFlow, we don't have to write this code, since we can use the function provided by TensorFlow. And I think that is a positive element for you. Okay, so the code is pretty simple. We use the method called image dataset from directory. In the first parameters, we have to specify the name of the directory in which there are the training data. In our case, training data are in the Euclid dataset, so I specify the name Euclid dataset. And then I have to specify where are the labels. And here I put the name inferred. This means that the labels are automatically created by this method using the folder inside the dataset folder. Remember that the Euclid dataset is divided into 4 different folders, so we can use this folder to automatically create our labels. So it's better to download and use datasets that are organized in this way, since you don't have to write the code to get the labels. So here I put the word inferred for labels, and then here I put the names. I put the names of the label that I want that correspond to the name of the folder. In this case, the code is able to understand that there is the class triangle that is in the folder triangle, the class rectangle that is in the folder rectangle, and so on. Okay. Then I have to specify the color mode of images, since in this code also images are open. So I have to specify the color mode, the color space in which I want to work. Remember the difference between gray level, grayscale, or intensity or RGB images. In this case, I specify that I want to work with grayscale images. Here, I specify the batch size. Remember the definition of batch size, the number of samples that we provide in input for each step, for each iteration. And here I specify the number 32. Here I specify also the size of the image that I want to input. And in this case, I want very little images, 32 times 32. But you can, if you want, you can also change these values. I specify that I want to shuffle my dataset, so you don't have to write also the shuffling procedure of your dataset, since you can apply shuffling directly in this method. So this method is fantastic, I think, since you can do a lot of operation only setting the right values. So shuffle equal to true means that we want to shuffle our training dataset. Then I have the seed number in order to have deterministic experiments. For example, I can reproduce the shuffling operation. Okay, the shuffling operation is a random operation. If I put the seed, a specific seed, I can recreate the shuffling operation. Okay. And then here I have to specify the split of the validation and also the training, the subset that I want to use with this method. In this case, I say that I want to create the training set using the 80% of data contained in my folder, since I put the 20% of data in the validation split. Okay. So remember that here you are defining the validation split, the validation set, okay, split. And after you are going to define the training split. Or you are going to define that in this code, you are creating the training set, okay? And then we have other parameters that are not important, since, for example, the interpolation, but they are not so important. If I run this code, you can see that, okay, this method has found 800 files in our Euclid dataset folder belonging to 4 different classes, since there are 4 different folders. And the 80% of this amount of data is used for training. So 640 files are used for the training phase. Here we apply the very same procedure to create the validation set. Okay, in this case, we are skipping the testing set. Okay, that's true. Only for simplicity. Remember that you have to also create the testing set, of course. For the validation dataset, we apply the very same procedure. So we specify Euclid dataset, infer, our label, and so on. The only difference is here, in which I have to specify that this subset is the validation subset, is not the training subset. Okay, but all the other parameters are equal. And then I can run the validation dataset. And as you can see here, the 20% of 800 files are used for the validation. So we have 165 images for validation. Okay, now it's time to build our architecture. In the scikit-learn package, you build this architecture using the first parameters that I show you. This parameter, hidden layer size, okay, in which you specify the number of layers of hidden layers and the number of neurons inside each hidden layer. While here we build our architecture, okay? We can build layer per layer our architecture. And we can say that, for example, we have a dense layer. Dense layer is the fully connected layer inside our multi-layer perceptron. In the first dense layer, there are 128 neurons, and the activation function is ReLU. Then we have a fully connected layer or a dense layer of 64 neurons, then 32. Both of them, in both of them, we have the ReLU activation. And in the final layer, we have 4 neurons, since we have to predict 4 different classes. So remember that the number of output neurons correspond to the number of classes. And if you remember, since we are in a classification problem, it's very important that the final activation function is the softmax activation function. Since here we need the probabilities. We don't know. We don't want to have logits, but probabilities, since we have to apply the cross entropy loss. That's why here the activation function is the softmax activation function. So as you can see here, we are recalling all the elements that I show you in the theoretical part. Here we have other 2 elements, and we are going to see these 2 elements, and then we can have the remaining parts in the next lesson. Okay. The flatten layer, we have already seen the flatten layer. Remember that in input we have 2D images. Remember that in input we have 2D images, X and Y, or columns and row. Okay, the multi-layer perceptron is a 1D structure. Okay, here we have the input. Here we have maybe the first hidden layer, then we have the second hidden layer, and so on. So remember, this is a 1D structure. This is a 2D structure. So we have applied a flatten process in order to transform this 2D image in a array, 1D array, in which element there is a pixel. Okay. So in the first pixel, for example, is here, the second is here, the third is here, and so on. So the flatten layer transforms the 2D input image in the 1D input structure of our multi-layer perceptron. Remember that here we have a multi-layer perceptron. Okay. Of course, we have to specify the input shape, that is the shape, the size of the input images. So 32 times 32. We have specified this size in the data loader part, if you remember. Okay. The last layer is the normalization layer. Remember that normalized and standardized data is a very important operation. With Keras and also TensorFlow, we can normalize data directly in our architecture, since there is a layer that, for example, the normalization layer that take in input the input image and then apply a normalization procedure, for example, using a specific mean variance, setting a specific mean variance. Okay, so here I put none, but we can also set that we want a 0 mean. And Unitarian variance, okay, in order to standardize our input data. So also in this case, you don't have to write the code to normalize data, but you can use a layer of our neural network to standardize or normalize data. If you not put this normalization layer in your architecture, remember that you have to write the code to normalize your data. You have to take all the images, and then you have to, for example, divide all the images using the value 255 in order to have all the values between 0 and 1, okay? Okay, so next time we are going to see the following part that are pretty simple, since as you can see here, also here we have the fit procedure, the fit step, in which we are training our model. But before we have to compile our model. As you can see here, we have to set the optimizer. In this case, we are using Adam. And you can see that also I'm specifying the initial learning rate that I want to use in Adam. And then I also have to specify the cross entropy loss that I use for my classification task. Okay, but this element, we are going to see this element next time. So see you next time.
Santa, sti viene. Pensare.